Conduction of heat. Here we have a solid, the red circles representing the particles within the solid. As they are heated, they will vibrate more vigorously, collide with their neighbours making them vibrate, and so on, passing these more vigorous vibrations along the line. So just to summarise, the higher temperature particles vibrate more vigorously. They make their neighbours vibrate due to collisions, and so on. Conduction works best in solids as the particles are close together and attached. Metals are excellent conductors as the free electrons within the metal can travel through the metal transferring energy. This is a much more effective method of heat transfer than the vibrating particles. Let's look at heat transfer by conduction across this block. If we say that the left is the high temperature side and the right is the low temperature side, energy will transfer in this direction from left to right. The rate of energy transfer, which I'll call delta Q over delta T, will depend on several things. It will depend on K, which is the thermal conductivity of the material. Some materials are very good at transferring thermal energy, such as metals, particularly things like copper and aluminium. Some things are very poor at transferring energy, like polystyrene. Copper, for example, has a thermal conductivity of around 400 watts per meter per Kelvin, whereas polystyrene a K value of just 0.08 watts per meter per Kelvin, around 5,000 times smaller. The rate of energy transfer also depends on the cross-sectional area A of the object. I've represented it here on the diagram. The bigger the cross-sectional area, the more surface there is for the energy to pass through, and so the greater the rate of energy transfer. Another factor is the thickness of the material, which I'll call D. That will be the thickness in this direction, the direction of energy transfer. Another factor is the temperature difference, I'll call delta theta, the difference in temperature between the high temperature side and the low temperature side. The bigger the temperature difference, the greater the rate of energy transfer. Putting these factors together leads us to the equation delta Q by delta T is equal to Ka delta theta over D, where delta Q by delta T is the rate of energy transfer, which will be in joules per second, K the thermal conductivity of the material, so a better conductor will have a larger value of K, the cross-sectional area of the object, the temperature difference between the two sides of the object, and divided by the thickness of the object. Let's just use that equation in an example. We're asked to calculate the thermal conductivity of a material if a square box of side length 50 centimeters and wall thickness of 1 centimeter loses 500 joules of thermal energy over a 10-minute period when at a temperature of 80 degrees C in a room at 20 degrees C. Now the best way to tackle a problem like this containing lots of data is to pull out all the data in one place and convert it into SI units. So that's what I've done here. Running through the question, we're asked to calculate the thermal conductivity of the material. So I've put down here K is equal to question mark. That's what we're trying to find. We have a square box of side length 50 centimeters, so each side will have an area of 0.5 meters multiplied by 0.5 meters, and there are 6 sides, giving a total area of 1.5 square meters. The wall thickness is 1 centimeter, and that is our D, which I've put down as 1 times 10 to the minus 2 meters, so this is in SI units. Our loss of 500 joules is our delta Q. 10 minutes we need in seconds, so I've put delta T is 600 seconds. And if the temperature of the inside is 80 degrees C, the outside is 20 degrees C, the temperature difference is 60 degrees C, which is the same as 60 Kelvin. A particular temperature in degrees C is not the same as the temperature in Kelvin, but as an increment of 1 degree C is the same as an increment of 1 Kelvin, a temperature difference in degrees C is the same as a temperature difference in Kelvin. Now I'll write down the equation and rearrange it for K. Now all that remains is to put in my data. So here it is. D, the thickness, was 1.0 times 10 to the minus 2 meters. Delta Q, the energy transferred, is 500 joules. A, the area of the box, was 1.5 square meters. Delta T, the time, of 600 seconds. And delta theta, the temperature difference, of 60 Kelvin, giving a K value of thermal conductivity of 9.3 times 10 to the minus 5 joules per meter per second per Kelvin. But joules per second are watts, so this is normally quoted as 9.3 times 10 to the minus 5 watts per meter per Kelvin.